Welcome back, students. Here, this is one more session regarding the stiffness method because, as you aware about it, as we have discussed earlier also, that this method is one of the best suitable method for the computer programmings. You may make a simple program for the any kind of the beam, which should be generalized one, and you have to just apply the some basic input parameters like loading, length, cross section, and the support condition, so that it will be give the output, and you don't have to change the every time. So many of the softwares are working on the stiffness method only, and that's why this is one of the most suitable and user-friendly method. So last time in the previous session, we have discussed about the analysis of the non-sway frame. Here we will consider the sway frame. What is the difference between the non-sway and sway frame? That it is a basically both are frame only, but in the sway frame, there is an additional unknown we have to consider as a that is a lateral deflection. While if you can compare with the previous example over here, that in the previous example, if we have seen, when we are neglecting the axial deformation, our unknowns or unknown displacements are nothing but suggest a rotation. We have not considered the effect of the any horizontal or vertical translations. So here we will see based on the one numerical solved example, you can feel that what is the difference between the non-sway frame and sway frame, and how it is going to differ in the calculation wise in the stiffness method. So let me start with a one practice example. So this is a one frame, portal frame, in which only in the column AB there is a this load is acting. So the we have discussed earlier the causes of the sway, that either if it is a length of the column is a different, or support condition of the column is different, or if it is a material or cross section of the columns are different, or if it is a horizontal loading is applied on the column, so that will be considered as a sway frame. So the complexity of the sway frame in the using the slope reflection and moment distribution method. So how the stiffness method is a more easier as compared to the earlier conventional method that we have to see. So let me start with the first step in this, and that is nothing but it's a KI. So first we have this frame. So what is a KI for this frame? At the B there will be three unknown displacement, and similarly at the C there will be three unknown displacement. But as we are aware about it here, for this AB there is a vertical displacement is considered as axial. For the this CD vertical axial, we have to consider. So if we neglect it, so here this we have to neglect. Similarly here we have to neglect this one, as we have only one member BC, and we have a two displacement, so anyone we can neglect it. So what is the remaining KI? Actually is a 6, and remaining KI will be this 3 only. So you can see the difference as compared to the previous example. Earlier we have considered only the rotations, but here in this case we have a some translation also. So here we have a three displacement. One, that is a rotation at B D1, which we have considered clockwise direction. D2, that is a rotation in a rotation at C in the clockwise direction, and in the D3, that is a nothing but it's a horizontal translation in the columns, and that delta we are considering in the right side direction. So with this, if we are compare or start with the example with the first thing and first step, there is a AD. AD is a nothing but it's a action in the actual structure corresponding to the unknown joint displacement with respect to degree of freedom. So in which you have to compare this entire frame with our actual frame. So if we go back and if you compare it, so it is just a one UDL is acting. There is no joint load specifically acting at the B or C, and that's why there is a whatever AD will be that will be nothing but a zero, right? As we have seen earlier also. So here, if we are considering in place of this UDL, along with that, if there is any kind of the horizontal load is acting at the joint, so that we can consider in the part of the D, D3 or AD3. because when we are considering the D3, so it is not a specific location, but it will be show the lateral deflection of the column AB as well as CD. So if any force which is acting at the B, right, or if it is acting at the C, both the horizontal forces will be considered as a action with respect to D3. So that thing you have to be keep in mind for the remaining all figures. So here in this case there is no moment at the B with respect to D1, there is no moment at a C with respect to D2, and there is no horizontal force at the in the column AB or CD. So AD is a nothing but it's a 0. Second, if we consider this one, action in a restraint structure ADL due to the load. So as there is a load is acting only in the span AB, so you may consider the friction moment of the AB, that is a 18 and 18 anti-clockwise, and along with that we have to find out the reaction. Why we have to find out the reaction? Because where we have a displacement is a horizontal displacement, so with respect to that we have to consider the horizontal forces also. So what is a ADL? So with respect to D1, what is a moment at B? That will be 18 clockwise. With respect to D2, what is the moment at C? There is a 0. And with respect to D3, what is the horizontal force at the B or C? So as we have assumed the right hand side direction, but here reaction will be in the left hand side. So this AD3 will be minus 36. So ADL is a 18, 0 and minus 36. Next, we have to find out the stiffness matrix. You have to just uh, there is a major difference you will see over here, because up till now whatever we have seen, that's only rotations, but along with this here we have a displacement is a horizontal translation. So whenever we are considering the with respect to D3, we have to consider the horizontal force at that particular points. So let me start with the first point. It is a D1, and D1 is a nothing but it's a rotation at B. So like we have considered in the previous example, that we have to rotate the joint B. So how it is going to deform? So it is like this, as it is we have assumed the clockwise rotation. So in the clockwise rotation, all the moment will be in the clockwise direction, and near end it will be 4 EI by L, and far end it will be 2 EI by L. Similarly, in the BA also 4 EI by 3 and 2 EI by 3. Now, one more thing, because of this rotation of the moment in the column, there is a some horizontal reaction. As you can see over here, there is a clockwise rotation of the moment. So here there will be anti-clockwise couple will be due to the reaction will be generated the anti-clockwise reaction, and the equation for that is a 6 EI by L square. Similarly, here if we consider for the beam, right, as it is going clockwise, so here also there is a reaction like this which will be form the anti-clockwise couple. But why we are not considering over here? Because we don't have any vertical displacement, we have a horizontal displacement, and with respect to that horizontal translation we have to consider horizontal forces only. So that's why we are not considering our unknown forces or reactions due to the rotation of the support in the case of the beam BC, but only we will consider in the case of the columns. Now, with respect to this, we will write the first column of the our matrix. We have a 3 point, which 3 point we have to consider as per this figure, that D1. With respect to D1, it is a we have to consider the total summation of the moment at B. With respect to D2, that is a rotation at C. So we have to consider the with respect to C, it is a rotation at C. We have to consider total moment at C. And with respect to D3, there is a horizontal translation. So total horizontal force is at the column CD or column BA at this location. So let's see one by one. The first one, total moment at B, that is a 4 EI by 3 plus 4 EI by 3, 6. That is a total, both are clockwise. So it is a 2 EI. Second one, that will be moment at C, that will be 2 EI by 6, and that will be nothing but 0.33. And third, we have to consider the with respect to this translation, we have to consider horizontal forces. So there is no force at the C, so only there is a 6 EI by 3 square, and that will be going in the opposite direction as compared to whatever we have assumed. So that will be minus 0.67. So that is the first column of the matrix. Similarly, second, We are considering d2 equal to 1, that is a rotation at c. Like we have considered in the previous figure, we have here the effect will be in the cb and cd, and at the near end moment is a 4ei by l, far end that will be 2ei by l. Similarly in the cd. So that is a moments. Now again we have to consider the forces because of the to balance this couple in the vertical direction of the moments. We will not consider for the BC. There is some reaction, but there is no use of that reactions as of now in this stiffness matrix. So here, if we are considering this is going clockwise movement, both the moment are clockwise. So reaction will be from the anti-clockwise couple. So here it is a right hand side, and here it will be left hand side reaction, which is a nothing but 6 by L square. Now we will see one by one with respect to D1 what is the total moment at B, that is a 2ei by 6. Similarly total moment at C, that is a 4ei by 6 plus 4ei by 6, so that is a 1.33. And with respect to D3 whatever total force is in the horizontal direction at the B or C, that will be nothing but it's a 6ei by 6 square in the opposite direction, that is a minus 0.167. So that is our second column of the matrix. Now based on the characteristic of the matrix we know that what should be the third column partially, that here as 1 3 will be nothing but it's minus 0.67, and s2 3 will be minus 0.167. But although we have to find out the s3 3, and that's why we have to go for the d3 equal to 1. We have to apply the unit displacement at the 1. So as we are going to apply the d3 equal to 1 at the b and c, so it will be like this. So it is a nothing but it's a sinking of support, settlement of the support at the, and we are applying the unit displacement the B and C. So here as it is going right hand side, so at the D it will be opposite to it. Both the reaction will be 12 EI by 6 cube. Similarly at the B also there is a right hand side it is moving. So at the A that will be going left hand side. So if we are considering over here, so frame is going to deflect something like this, and both side it is having the same amount of the deflection. Is apply the unit displacement of the 1 mm. So that's why it is we are considering the reaction in the both the columns, and the reaction is a 12 ei by l cube. Now on the both the side along with the reaction, as you can see both the couple right over here it is a forming the clockwise moment, right? As we can see this couple and this one, so it is a forming the clockwise moment. So we are providing the anti-clockwise moment as a fixed moment. Okay, so it is a 6 a by 6 square both anti-clockwise. Similarly in the BA it is a anti-clockwise moment 6 a by 6 square. Now here as we are on the verge of the last column, so let me see what is a moment at B, that is a 6 a by 3 square, but as it is an anti-clockwise moment here we are assuming the clockwise, so it is a minus 0.67. Similarly moment at C, that is a anti-clockwise 6.6 6 a by 6 square minus 0.167. And last one that is a D3 S33. So as it is a horizontal displacement, the total horizontal force at the B and C, that is a nothing but S33, that is a 12 EI by 3 cube and 12 EI by 6 cube summation. It's a 0.5 EI. So the final matrix is this one. So this matrix we have to use for the further calculation. So that is D equal to S inverse AD minus ADL. We have to do the inverse of this matrix, and that is going to multiply with a minus 18, 0 and 36. So final answer will be 1 by EI 26.74, 7.21 and 110.24. So what is the indication of this? That first two are indicating the rotation at B and C. Third is nothing but it's a horizontal deflection at the B and C. So that is a nothing but 110.24 by EI. So this is our primary unknown to rotation and deflection in the horizontal direction. So here that's a major difference you can see in the non-sway and sway frame, that in the sway frame that additional unknown is nothing but we have a horizontal deflection along with the rotations. Now we have to find out the member and action. So like we have done previously, that in the sequence we have to consider all moment in the clockwise direction: am1, am2, am3, am4, am5, and am6. Now this, for this we have a two thing, AML and AMD. For AML we will consider the fixed moment, ADL figure, right? And in the sequence we will write, as it is 18 is anti-clockwise, so minus 18, 18, 0, 0, and remaining 2 also 0. Similarly, AMD, in the AMD there will be, we will consider one by one figure, d1 equal to 1, d2 equal to 1, and d3 equal to 1, one by one. So first one, it is a 2 by 3, it's a 0 0.67, 4 by 3, 1.33, 4 by 6, that is a 0.67, and 2 by 6 is 0.33, and last two are the 0, 0. Second column, d2 equal to 1, same figure we have drawn earlier, so that is nothing but over here 0, 0, 0 0.33, 0 0.67, 0 0.67, and 0 0.33. Last, d3 equal to 1, horizontal displacement at the column, so it is a anti-clockwise all four moments, and there is no moment in the BC, so we have to consider minus sign. So this is our AML, AMD, and D is ready, and we have to multiply the this AMD into D, and then we have to add in the AML. So the final answer for this will be like this: minus 73.94, minus 20.29, 20.29, 13.6, minus 13.6, and minus 16. So if we put along with the direction, so it is like this: first two are the minus, so both are anti-clockwise; second two are plus, both are clockwise; and third two are the minus, that is why it is a both are anti-clockwise. So the final bending moment diagram will be something like this. For the support moment, as all are generating couple, so it is a changing the sign from the minus to plus in the each member. Along with that, as it is a UDL, so we have to draw the here parabola of the WL square by 8. So that is a complete bending moment diagram for this waveframe. So with this, we are ending this session, and you may share your doubts and queries in regarding this example, or for any question to me or in the comment section. Also, you may share your valuable feedback regarding these video sessions, which we have seen for this course in the comment section. So thank you so much, and uh, please let me know your valuable feedback.